So in this video, we're going to look at the meaning and origin of the equilibrium constant. And we're going to do so looking at this very important reaction in the earth sciences, where we take the mineral magnetite, 2 units when written in this type of formula, and it's going to react with 3 units of quartz. We'll write that as Q. And it'll react to make 3 units of phthalate plus 1 unit of oxygen gas, which we'll just write as O2. This is otherwise known as the so-called oxygen buffer, QFM for quartz phthalate magnetite, or FMQ. You can reverse the letters, it's still the same reaction. Phthalate magnetite quartz. Doesn't matter how you write it, it's the same thing. So if you see these letters QFM or FMQ, it's referring to this kind of reaction. So how did we think about it in the 19th century? The way people were thinking was in terms of Newtonian mechanics, where you had forces. So the state of equilibrium, just to abbreviate that as EQ, is the case where the forces that would push things to the left would be balanced by forces that push things to the right. You could also think of it in terms of rates. So sometimes instead of an equal sign, you write 2 little arrows or half arrows. And so that's to signify that we have this reaction that can go in either direction, and equilibrium would be not only thought of as a balance of forces, but also a balance of rates, where we make this stuff over here on the right-hand side as fast as we make this stuff. And so if the rates are equal, the forces are in balance, then we are at a state of equilibrium. So how would we write the forces? The forces were thought of in terms of concentration. So forces would be proportional to the concentrations of the various components. And so we can write a force, or let's think about it as a rate. So the rate would be equal to the concentrations of stuff on the product side multiplied by some rate constant. Let's just call it K1 for the right side. And then another rate could be the forces on the left-hand side. So that could be K2, and then C for reactants. Let's write that a little more explicitly. So using the same formula, we can think of a rate going to the right, and that rate would be equal to, let's just call it rate constant C1, would be the concentration of magnetite multiplied by the concentration of quartz. And then we have a leftward rate, and that would be some other rate constant 2, not the same as K1, and it would be proportional to the concentration of oxygen gas multiplied by the concentration of phthalate. Doesn't matter what order we take the product. And then at equilibrium, those two rates should be the same. Now it ends up that it's not just any rate, it's not just any concentration. A little bit of experimentation in the 19th century showed that the best way to describe the rates was not just the concentrations themselves, but you get a little bit better description of actual data when you take these concentrations and you raise them to the power of the coefficient. So if you go back in the video, you'll see that magnetite had a coefficient of 2, so we'd have an exponent of 2. And then for quartz, we had an exponent of 3. And then phthalate had an exponent of 3 also. And there was, we don't need an exponent for O2 because its coefficient was 1. So we could take the cube of the quartz concentration, multiply it by the square of magnetite, and then multiply it by K1, and that would be our first rate. And then we could take the concentration of oxygen raised to the power 1, I guess we could put that there for completeness, and then multiply it by the cube of phthalate. And so these would be our rates for the rightward and leftward forces. Increase the concentration of magnetite, and you increase the force, and hence the rate at which the system would move from left to right. So then you can write this so that the rates are equal. So we can have K1, which is the concentration of magnetite squared, and then multiplied by the concentration of quartz cubed. That whole product would be equal to K2 multiplied by the concentration of oxygen gas, and then the concentration of phthalate, also cubed. And so this would define, when these rates are equal, that would define the state of equilibrium. So now you can divide things out. You can take K1 divided by K2, And with a little bit of algebra, we would say that that is equal to the concentration of O2 gas multiplied by the concentration of phthalate raised to the third power. And then that would be divided by the concentration of magnetite, also cubed. Oh, excuse me, that would be squared. And then that would be multiplied by the concentration of quartz, and that fellow would be cubed. Let's get rid of this guy here. So this guy here would be our so-called equilibrium constant. It would be a ratio of the two rate constants. Now these rate constants are not the same. Again, K1 is not equal to K2. They are different numbers. So this is not something that would necessarily equal 1, although I guess in theory it could. So the equilibrium constant would be that ratio of rate constants, K1 and K2, that would give you an equal set of forces pushing things both to the left and to the right. That equilibrium constant could shift as a function of pressure and temperature. But if we hold pressure and temperature constant, then there is only one value of the equilibrium constant that should obtain. What else could we vary besides pressure and temperature? We could vary these concentrations, but if we did, those would only push the system to go back to an equilibrium state where this ratio would then still be the same. Remember, K1, K2 is also this continuous product of the products, in this case oxygen gas and phthalate, divided by the reactants, in this case magnetite and quartz, not very neatly drawn here. So that's the equilibrium constant, the way people thought about it in the 19th century, and to a degree the way we still think about it today. In a later video, we'll look at how these concentrations can be thought of in terms of activities, which we write as A, and how we can relate the entire equilibrium constant to a difference in Gibbs free energy.